For this problem, we're going to be looking at an H2O blob that is liquid. We're told the pressure is 23 megapascals, and we're told that the temperature is 160 degrees centigrade. We're obviously going to use the state postulate. So given two independent intensive thermodynamic properties, the others are determined. We can find the specific volume thus. So our governing equation is the equation of state, which is the buy two get one free principle that is determined by the substance and the phase. So in this case, we have the, let's take a look here. If we look at the possible tables for liquid water, we are going to want to use table A7, and the table is our equation of state in this case. So if we take a look at table A7 real briefly, and we look all the way down here into, let's see here, there it is, table A7. We look and we see there is no 23 megapascal isobar data. That data would exist in this seam if it was there. So instead what we need to do is create that data. So let's go ahead and take a look at what this might seem. We'd have 20 megapascals, and at the same time we have the 30 megapascal isobar data, but we don't have the 23 megapascal isobar data, which is what we want. At the same time, we do have, at a temperature of 160 degrees centigrade, we do have the data for the specific volume. It would be 0.00108886 meters cubed per kilogram. So these are all volumes here that we're going to be looking at. And the pressure when it's 30 would be 0.001083 meters cubed per kilogram. So we want to interpolate between these quantities to be able to find out what is this value going to be right here for the 23 megapascal isobar data. So what does that look like? Let's go ahead and start up a little file here. We'll call it tableEOS.m, and we'll also go ahead and start up MATLAB. And let's go ahead and we'll start as we always do with the secret sauce inside our M file, and we're going to just use our interpolation function, interp1. So we're looking for a volume here, and the volume is going to be an interpolation, and we're going to interpolate for our independent variable here, which is the volume. We're going to interpolate between 20 and 30, and our dependent volume variable, well, let's cut and paste that directly out of Single's table. That way we don't make a mistake. So open bracket here, and then the first value, followed by the second value at 160 degrees centigrade. So let's plug it in. And then we're interested at the pressure of 23 megapascals. And let's go ahead and run this very first file. There we go. Oh, and this is not called interp, but interp1. And we can see that the value that's been interpolated for us, so the value that would go right here, is 0.001087 meters cubed per kilogram. That volume is in between 0.0886 and 0.823. So we know that we've interpolated correctly.